Hello and welcome to the task Perlin Planet. In this task we are using Perlin noise to create this procedural planet, as we can see here. Here we can see the initial state of the task, where we have this low polygon sphere with some noise on it, but in the end we want this to look like this. So there is this shading here, the atmosphere has a bit of a glow, the islands or the land masses have different colors on them, and the sea has specular highlights. So all the details and the steps are here, both for JavaScript and C++. And also there's this hint on how to create this atmospheric glow as well. If you go to the code, you can see that the code consists of 4 files. We have our index as usual, then we have the main.js, that's where we give different colors and also uniforms, but the main part of the task is in the fragment shader. So vertex shader we don't really use, but the fragment shader, there is this hash function, the noise function, and the main function. So the hash function is just a pseudo-random number generator, which takes in the position of the vertex or whatever position you want this to be, and gives out some random one-dimensional value. And the noise is just the implementation of the Perlin noise. We can also see that the U that is used here uses the Hermite interpolation. And we can see later what happens if we use linear interpolation. And in the main function, we will just fulfill the steps that we saw. So there's the task 4 to 8 here. But the first 3 tasks are in this file. So let's create a sphere. And the first thing that we have to do is the current sphere has few polygons. So if I show you the result of the code right now, it's just a very low polygon sphere. You can actually see angles and no planets like that. And what we have to do is make the sphere look smoother by changing the geometry values. So actually what we can do is change this material first so that we can see the geometry as well. So if we do wireframe and set it to true, then we can see the polygons themselves. So we can see that not many polygons actually are in use right now. But if I increase those values here, so for example, instead of 8 segments and 6 segments on X and Y coordinates, I'll use 18 and 16, so now I have even more polygons. So if I comment this out again, then it's a lot smoother, but not smooth enough. I can still see that the corners are flickering in and out. So maybe I will do like 48 and 46. But now it looks very smooth. And if I look at the wireframe, you can actually see that there are lots of vertices and triangles. This sort of sphere has lots of triangles at the tips at the poles, and the equator is actually much lower quality. So one thing you could do is, instead of using this 3GS sphere geometry, use icosphere. And that's especially useful if you have a project you are using and you want to change the height values as well of the planet. But anyway, that should be good enough. Keep in mind that if you raise these values, the GPU does more work. So for example, if I do 100, and then there's lots of triangles, but the GPU will do lots of lots more work, and it might not even be worth it to do that work, because 48 and 46 should be good enough for this task at least. Okay, so that's the first task done. It looks smooth now. What's the second step? So the second step is merge multiple noise layers to cover the planet with the true Perlin noise. So that's actually in the fragment shader. That's the task 4. But let's first do a setup where we give the uniforms as well. So one thing that we have to do is add the phone core plin lighting as well. We see the specular highlight. So what we need is a light position. And light position currently is just this constant here. I think this is in world space then. So we can do light position, and that will be, the type will be vector 3, because it's a 3-dimensional vector. So the value will be, oh, apologies, light position. So now I have light position uniform. I can implement the lighting model here. But that's not the only thing that we have to give to the fragment shader. We also have to do different colors that the planet will use. So we have the color for water. So that's the water color. That will be this blue. Then we have the color for atmosphere. So this is the even lighter blue that we use for the glow of the atmosphere. And then we have 3 colors for the terrain as well. So currently we can see that it has like light green and dark green, but if we zoom in closer, there's this small spot of brown as well. So there's a brown color as well. And this is a creative task. So you can change those colors to whatever you want. You can change the color of the water. You can do anything. You can even add more colors if you wish. As long as it looks cool in the end. So we can pass the colors as uniforms. So first let's pass the water color and the atmosphere color. So firstly we use the color water. Oh, we had to add the comma here. And the type will actually be the same as the light position. Well, actually it's a color, so it's C. And the value will be this. And I can repeat this for the atmosphere color as well. So now I have this terrain colors as well. So for that I will use the color vector type instead. So let's first copy and then change this. So it will be colors. Because I don't want to create an individual uniform for each of them. I can actually put them into an array. So instead of using C, I will use CB, which is a color vector. And the values have to be an array. So I can add the colors 1, 2, 3. So now I should have these uniforms in my fragment shader if I add them. So just in case I will check if I have any errors. Nope, don't have any errors. So now in fragment shader I can add those uniforms here as well. So let's add the uniform for our light position first of all. So that will be used for the light calculations, but we also have the color of water. And also color atmosphere. And then I will have the array of colors that I can do with this. So now I have all the uniforms available. Let's see. Oh, there is an error. So color simplicity size the arrays only out the selections here. Okay, so guess I can add the value. Yep. So I have to specify the size of the colors array here. Otherwise, it's an error. Okay. So I guess now we can continue with the steps of the task. But first, let's think about this noise. So currently, what we have to do is we have to add different noise layers together with different weights. So and each different noise layer will use different frequency of the position. But let us think about what's the maximum and minimum value of the noise itself. So let's figure this out on the whiteboard. So during the Perlin noise calculations, we have this square, right? And then we have the gradient vectors as well on each corner. So let's analyze this corner specifically. and let the size of the square be 1, then the gradient vector will also have a size 1. So it will be like this. And it will follow this circular path. So that's the possible values of this gradient vector. And where on this square would the minimum value be? So it would be in the middle here somewhere. That's because the gradient value or the noise value is calculated by the size of the gradient vector times the size of the v. So let this v be the vector from the corner to the center point, and then it will be multiplied by the cosine of the value between the v and g. So v and g. Aka it's a dot product between v and g, normalized values of them. And if the g is always 1, then we can just replace it, and v will be, what will v be? So the v will be in the center right here. What's the center value here? So let's use the Pythagoras theorem. What's the size of the diagonal? Diagonal size is the 1 squared plus 1 squared, and then take root square, and then we have to divide by 2. And then what we get is square root of 2 divided by 2. And that's actually the maximum value of the noise that we can have. And the negative, the least value would be the negative square root of 2 divided by 2. And that's when the gradient vector is pointing the other way, because then the cosine will be negative 1. And remember, cosine is 1 if the angle is 0. So that's why the point has to be in the center. And if we expand this to a higher dimension, then the center point will be distance 3, root square 3 divided by 2 away. So that's why the maximum and minimum value will be, I think actually will be inclusive. It will be square root t divided by 2. Well, then that's the negative value, and then square root of t divided by 2 is positive value. So that's the range of the values that the noise will generate. So keep that in mind when you compare different values together. Those are not actually between -1 and 1. When you can normalize these values, then you can use different functions that actually require values to be between 0 and 1. For example, Bernstein interpolation becomes usable with the noise input if you know that the value is between 0 and 1. And you can actually normalize the noise value between 0 and 1 when you know the minimum and maximum value of the noise. So coming back to this code, now we know that the noise value will be, so we are using the 3-dimensional noise value, so it will be between minus square root of 3 divided by 2, and then the maximum value will be 3 root square 3 divided by 2. So when you return this, you can actually normalize it in this function as well. You don't have to do it here, but we might actually want the negative values as well. So that's your decision what you will do here. Currently, just keep it as is, because we don't really use any functions, but that require normalized values. But one other thing, the u here that we are using as input for the noise, this noise equation here, we are currently using the Hermite interpolation. So let's see what it looks like. It looks like this smooth values, but if instead of using the interpolation we just put the f, then it's much more like squared off. That's when we are using the linear interpolation, and that's not what we want to use. We want this to be a lot smoother, so that's why we are doing the Hermite interpolation. So here in the materials, under the procedural generation, there is this demo here that actually shows what different interpolations look like. So currently I'm on the layer 2 and I'm using linear interpolation, so it looks very blocky, squares everywhere. But if I use the Hermite interpolation, it looks much more smoother. So that's why we are using Hermite interpolation. There's also a fifth order interpolation, which looks even more smoother. So for example, if I show the sum of all the layers, the difference between linear and fifth order, there's this subtle difference that the linear is a bit more blocky compared to Hermite and fifth order. And so you can actually change the value between Hermite and fifth order, or you can use another function here as well. But currently, we'll just use the Hermite, because that's really good. So yeah, this is a smooth sphere now. But let's do the task 4 now. So calculate depth by combining multiple noise layers using different density. So right now we are just using this single layer. You can copy this formula here and then use different values here. So I'm reducing the weight here, but I will increase the frequency. So it will be a different noise with lesser contribution. So now if I comment this out, actually, let's see the difference. So that's the new value here. So if I remove this, it looks like this. When I add it back, it has this more detail, more peaks and valleys. So I can repeat this. So we might like 0.2 now, and even higher frequency like 12. So it has even more detail now. And let's add one more layer. So here you should actually pick your own values here, depending on what sort of planet you want to create. So currently this is just experimenting with different values here. But you should definitely pick your own values. Don't copy these values. Those are just random. They might not even look good. So you can actually add more layers as well. So currently I'm using 4 layers. You can add even more. And if you want to normalize these values as well, then keep in mind the maximum and minimum values of the noise and also the weights as well. So yeah, now I have this combination of noise values. It looks a lot more noisy. So now I have to determine the color of the fragments. So what we need is determine what is sea and what is land, and at land what is dark green and what is light green and what is brown. So we can do that by just using thresholds. So for example, by default, let it be water. Now we can use the uniform and then render it here. So now it's just the color is blue, so everything is water. But now we can add this if clause here. If the f is larger, f is larger than 0, then we can change the color value to be maybe color 0. So now there's the color is not uniform because it's colors, it's plural. The color itself is the vector. So still no result. Let's see. Wrong operand type, no operation exists, left-hander, high float, constant. Okay, so this has to be float. So yep, now I have this. So I have land that is green and then I have water that is blue. So I can actually change this value as well from 0 to 0.2 maybe to add more C, or I can actually reduce it. So 0.2, negative 0.2, then this more grand. But let's just keep it at 0. And we can add even more thresholds. So if it's greater than 0, then it's this. But before that, let's check if it's greater than maybe 0.5. And in that case, let the color be the brown color. And now we just add else here. There are very small spots. Oh, there is this big brown spot here now. So there is at the south pole as well, lots of brown there. So now I have like 2 layers. I can add one more layer between them, that is this dark green. So that will be maybe 0.2, like we saw before. So now it has even more variety. So you can change those values between different values. The other thing you could do is use the Bernstein interpolation values, so the 3 values, and then interpolate between the colors themselves. So it will be the transition will be smoother. This would look really cool, but we saw how to use the Bernstein polynomials in the animation part of the import the chopper task. So you could use this here as well. And it wouldn't even be very difficult. But for that, the f has to be between 0 and 1. And don't interpolate between watercolor and land color. That would look strange as well. But currently it looks nice. You should add more layers, of course. So currently it looks very cartoony. But in the task, it has this much more high frequency and small islands everywhere. So maybe I make this look like this or something else. So you have to decide what it will look like. So the next task will be add the Fungor plane lighting model. So that's for you to add. And then add specular highlight to the water, but not for the lens. So figure out how to do that. And then finally we add the atmospheric glow effect. So the glow effect will look something like this. So what we do is we compare the vector from the viewer to the normal vector. And when the dot product is closer to 0, then we add this glow. So I can actually demonstrate it on the tablet. So here, let's just draw a sphere. And then let's think about the normal vectors. So normals are pointing in perpendicular direction compared to the camera's or the viewer vector. And that means that the dot product between this vector, so one of this n vector, and the viewer vector, which is from the perspective of your eye, will be 0. And we can use that value to say that when the dot product is closer to 0, then there is a glow, but when it's closer to 1 or -1, so you should compare the absolute value then. When it's closer to 1 or -1, then the glow shouldn't be there. But also you should take into account the direction of the light source as well. Because if, for example, light source comes from there, then shouldn't be any glow here. Because the light just can't reach that place. So there shouldn't be any glow there. So try to figure this out. And we can actually see in the task description, that's how the glow effect should look like. And yep, that's the last thing you have to use. So yeah, use the cosine angle between the vector towards the camera and surface normal. And the glow should be stronger when the angle is close to 90 degrees. So that's exactly what we want to do. And if you have added this glow to the planet and it looks really cool, maybe something like this or something even better, then the task should be complete. So good luck solving this task.